Alright, so wrap up whatever you're working on for the next minute. If you're kind of completing or embellishing or adding examples, adding units. You might even draw some pictures, but the examples that you have in there are real life examples, and then you have some solutions. You have some examples like solution-based examples. Alright, so now flip back to your Graham's Law page. And this equation looks a little different than what we've seen in the past because it relates to effusion, so it relates to speed. Can anybody remember what effusion's definition was? We wrote down diffusion. CJ's table. Right, so hopefully my image was prompting you to think of that. All right, everybody's back with me on Graham's Law page. You good? All right, so we're going to write down effusion is escaping of a gas molecule, that abbreviation for molecule, through a hole. And so that's, obviously a great example with a balloon. But if we have a balloon and we blew it up, think about this. We have a balloon and we blew it up. What kind of gases would be in that balloon? Shout it out. So carbon dioxide, what else? Well, maybe because there's obviously some residual oxygen that's going to be accompanying that CO2. What else? If you breathe it in, yeah, maybe some nitrogen. Give me one more. Your saliva is primarily composed of water, and you have some hot breath, right? So if you blew on a piece of glass, you would probably be blowing out some condensation as well, right? So say again? Some water vapor. Okay, so these are all, let's say, in our balloon, those are all the gas particles or types of gas that we travel in. So CO2, oxygen, nitrogen, and water vapor. Which of those do you think can travel the fastest? Think of an example, like think of a running back versus a lineman. Who's going to run faster? Running back, okay? So why are we saying that? Sorry, yeah, smaller things usually move faster, and that's the No, go sit back down. We're in the middle of notes. That's one thing you do on your own time. Sit down. So in terms of what we're looking for size is going to matter here. So which of these particles are you thinking is the smallest? Don't just look at like general size. What do you think we should calculate? Their molar masses, right? So everybody, you have maybe a periodic table nearby. Do just a little quick mental calculation of these. So we have CO2, O2, N2, and water vapor. Somebody at your table can do one of each. All right, come back to me. 3, 2, 1. Dunn's table. Tell me one. So that's about 18 grams per mole. Bryce's table, another. Okay. And up here? Chris's table, another. Okay, so I'm just rounding you guys. Obviously, you guys can see that, right? Back table. Carbon dioxide. 44.01. Okay, so we've got about 44 grams per mole. All right, so which of these is going to move fastest? Who's our number one, the fastest gas we have? H2O, right? Okay, so we're going to say, I'm not on my example, I'm just going to put number 1 there. Just drop it on my desk, take a seat. So that's our fastest. Who's our slowest? Who's number 4? Carbon dioxide moves the slowest, right? Okay, who's in the middle? Who's number 2? So we have 18 and then 28. That's our next lightest. That's number 2, and so this one must be number 3. So what we can say is, okay, when we pop the balloon, and it pops, and gases start to escape, who's escaping first? Who's moving the fastest and getting to the hole first? Water vapor starts to come out first, okay? And then what's going to be the last thing to kind of leave? Carbon dioxide. So if we pop the balloon and we let some gases escape, the last thing to remain being CO2 means that it's the one that's going to be holding the balloon kind of together. Because you know when we pop it and we like let it shrink down, it kind of gets down to this like ugly looking wrinkled balloon. What's holding that balloon together though? What's holding the balloon slightly inflated? CO2, because it's the last thing in the balloon. So this law is all about masses and how fast, or the velocity of those gases. So it is related to kinetic energy, because the kinetic energy is the energy of, everybody? Kinetic energy is the energy of motion, right? So we're talking about things moving, so this is the energy of motion. And so it is inversely related, mass and speed. So this is mass and velocity. This is not Graham's law. This is just the relationship that we're using to establish Graham's law. So if your mass is high and your kinetic energy, it has to be a constant value, because kinetic energy is related to temperature. We're assuming all these are at the same temperature in this particular balloon. If your mass is high, what does your speed have to be? High or low? Low. Heavy things move slow. Little things move fast. That's the relationship. Give me a thumbs up if you're good with that verbal relationship. If the mass is high, the velocity is low, or vice versa. If the mass is low, the velocity or speed is high. Okay, so as you can see, according to the definition you wrote down in Graham's law, the rate of diffusion of any gas is inversely proportional to the square root of its molar mass. Okay, so we're literally going to write that down here in the formula. The rate of diffusion is equal to the square root of the inverse of the molar mass. That's it. That is Graham's law. But rate of diffusion, if it makes more sense, you might want to put velocity or speed, because again, we are talking about how fast those particles are moving or diffusing through a hole. A lot of times, though, this is of course for one gas. So I could say like gas A. This would be the molar mass of gas A. Many times we don't compare one gas. Like for example, I compared 4 up here. That would be very challenging to do in this situation. So most of the time we compare 2 gases at a time. So I'm going to write the comparative version of that. And this is the one we use most often, so this is the one I would think that you would probably remember. So we'll say rate of gas A over rate of gas B is equal to the square root of the inverses of both of those masses. So molar mass of who should go on top? B, because it's right inverted in that fashion. Molar mass of B, and this is molar mass of A. So this is probably what we'll use most of the time for Graham's law, but we're deriving it from this idea here. Thumbs up when I can move on to examples. Okay, and obviously these examples, if you want to put them on your foldable, you're good. But if you can't squeeze them on there, do not do it so that you can't read it, right? Ready? Okay. So this is the one we'll likely use, but it depends on what the question is giving us information about. Oh, I like this example because this is at the Macy's Day Parade, and they had some small holes in their float. And so they had to really realize what was still in it, how long was it going to take for them to deflate, so someone could figure out how long they need to stay there for that energizer running to deflate all the way so it could take away. So that's definitely an application of Graham's law.
Ms. Admiral?
Yes?
Could I please have Corbin Washburn for dismissal?
Thank you.
Thanks.
Listen, Katie. All right, so we're reading, we see the relative velocity, right? So that's talking in comparative fashion between hydrogen gas and carbon dioxide gas. You guys with me? Okay, so here's my tip for you. Anytime you're doing this, you're doing A versus B, make A your lighter gas. So see if you can set up that proportion like we just did on our the equation we just set up. Walk around calculators for me if you need a calculator. He's rolling fast, but grab and go. Alright, so we're working with hydrogen gas. Is that hydrogen gas right here? No, it's H2. Good. What's the molar mass of hydrogen gas, everybody? Give me an approximate here. About 2 or 2.016, right? So 2 grams per mole. Got it. CO2, we've already done that calculation. What's the molar mass? 44 grams per mole. So we definitely have a situation where one's very light, so it's very fast. One's pretty heavy, so it's pretty slow. So the relative rate of comparison will be rate of who over who. Who's going to be on top? Hydrogen. So I told you the best bet to make sense of what we're talking about is put the lighter one on top. So that's going to be hydrogen gas. CO2 will go on bottom. And then we're going to set it up with what on top? Good, it's inverted. So CO2's mass will go on top. That's 44 grams per mole. And who's going to go on bottom? The hydrogen gas. All right, so I know that you can simplify 44 divided by 2. What is that? 22, right? But I don't necessarily know the square root of 22, hence why you need a calculator. You could guesstimate it's around, I mean, that's almost 25, right? What's the square root of 25? 5, so it's going to be about around 4.5-ish, 4.6-ish. What is it? 4.69. Okay, so the answer of the relative rate of diffusion is 4.69. Notice there's no units, right? Because these grams per mole cancel out. But what does that mean? So you can come up with a sentence using that number that describes the question within your groups. Okay. I'm going to ask for our group to give me a sentence on what they think this means. Ready? Bailey's table, give me a sentence. What do you guys think? Bailey's table. That doesn't really tell me anything, but if you're repeating the question, give me a number with it. Doesn't tell me anything. Arian's table. Make it make sense though. Like, why are we comparing these velocities up here?
Hydrogen gas diffuses 4.69 times faster than CO2 gas.
Okay, I'm just going to say H2 gas is 4.69 times faster than CO2. And we know where it's obviously it's in relation to fusion, but that makes more sense now. This thing is pretty light, but how much lighter is it? How much faster can it move? Hydrogen gas can move about 4.5-ish times faster than CO2. Does that make more? Does that put into perspective at least? While we're doing this, okay. So that's a type of sentence you could rephrase that to be. Okay, so now I'm providing you with the rate of diffusion. Like the relative rate of diffusion is 4.5 times the rate of krypton gas. Sorry, the unknown elemental gas is 4.5 times faster than krypton gas. What is the molar mass of the gas? What's the identity of the gas? So think about what I've not provided you. Set that as X in your equation. See if you can figure it out. So basically, the two styles of questions that would be asked in that relationship to Graham's law. Definitely want to think about who is A and who is B here based on the phrasing provided. Think about who is A and who is B based on the phrasing of the question. All right, so 4.5 is our rate, that rate A over rate B. So that is rate A over rate B, because that's saying A is moving 4.5 times faster than B. But we actually know who should be A and who should be B. I told you A always has to be the lighter one. So elemental or krypton, who's lighter? Elemental, because it's saying it's moving that many times faster, or the rate of krypton gas. So this is the faster one. So this one has to be A. So we'll keep A as an unknown because we don't know that one. So we're inverting or making an inverse relationship with the molar mass, where krypton gas has to be B. So I'll put even like krypton right there to recognize that's its identity. So what's the molar mass of B or krypton? 80. What do you say? 80 what? Oh, 83.80 grams per mole. Okay, so now we have this. So let's kind of dumb this down to just the math. So this is 4.5 is equal to the square root of 83.8 over x. How do I get x out? What's the first step I should do? Say again? Okay, so I can't pull x out because it is currently being square rooted. So what should I do first with the square root? Square it. You need the opposite of square root, which is squared. So we're going to square both sides of this equation, which is going to cancel out the square root to leave us with 83.8 over x is equal to, what's 4.5 squared? 20.25. Okay, so we made it there, and then now I need to just rearrange this equation to solve for the one unknown. So then x, how do I get x out? Times everything by x. So I need a times x on both sides because it's currently being divided. Times x over here. So that side cancels. So then x is now currently coupled with this one. So how do I get rid of the number? Divide by 20.25 on both sides. Okay, so x is equal to 80.8 or 83.8 over 20.25, which is about what? 4.13. Okay, grams per mole, because remember this was a molar mass. So this is the molar mass of A. Who or what elemental gas has about a 4-point-ish grams per mole? Helium. So you make sure that it's a gas, because we're definitely still dealing with gases. Those are the ones that are fusion. And helium is our closest bet. Yay! Alright, give me a 1 out of 10. How do you feel on grams? Those are really the only two styles of questions that could be asked about. Okay, so take a minute to, if you need to add any more detail to your foldable, I'm going to show you this cool Mythbusters video. Make sure it's going to pull up right on effusion. Did I pull up the right one? I need to make sure this is the right one. Let me make sure before this is a plain one. Let me just Google this. I thought I saved the right link. Hexafluoride. Okay, here we go.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
Well, simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that, and I guess that's why I love, although somehow I'm still funny. It's scientific!
So how do you think you should, actually, molar mass. What's the molar mass of sulfur hexafluoride? Cancel. Sulfur hexafluoride. Sorry, I'll turn the lights back on. Sulfur is what? 32 is. Fluorine is 19 times 6. Guys, you can do that probably in your head. What's 20 times 6? 120. What's 120 minus 6? 114 plus 32. 146. That's pretty heavy, right? We're dealing with oxygen and carbon dioxide in our lungs, which is like, what, 32 grams per mole and 44 grams per mole? Sulfur hexafluoride, which is 146 grams per mole, is going to sit in the bottom of your lungs. So how do you think you should get that out of your lungs if you did that, which we would? I mean, you keep breathing in and out, but it's still pretty heavy, right? How could you get it out the bottom of your lungs? Huh? Just do a handstand. Yeah, just get it out of your lungs that way. Not that I'm encouraging you to do this, but you definitely could get it out if you needed to. All right, I'm giving you a quick break. If you need to stand up, we're going to do a couple more notes together. But if you need to also review if there's anything else in your focal, now is the time. If you have your problem set out, you can look at the problem set for a minute and see your brain start to continue. We're going to do 3 stoichiometry problems with gas law. So I'm going to do 3 regular parts. Do I need to pull up the instructions for the foldable? You have definition, formula, example in real life, and a sample problem. That sample problem, we probably did a lot of those in class, but there may be one that you need to add. And then you have on the front this information, including effective use of color. This is not a just copy situation. Go with your notes, go through your notes. Guys, I'm literally giving you a chance to finish this right now. If you're just sitting there big chilling, I'm gonna leave you 0. What you getting from me?
The units to the unit as constant. What this means is you have the equation down. And so pressure must always be equal to this. Pressure volume must be equal to this. Amount must be equal to this.
You should have that in your notes.
I'm saying I'm not sure if that one, this one, this thing right
If that's what you're writing down as your standard pressure, yeah.
You'll need to convert the units to the universal which is pretty much just those units that you use. Yes. No, it's not that. It's basically just saying that you need to use the same units when solving the equation. Like you need to use it. Which is probably Celsius constitution.
Give me a thumbs up if you're done with your foldable and you feel happy with it. It's got everything that's required. Alright, take 1 more minute then. You need to grab a color, marker, highlighter, whatever. Do that too. And if you're looking for sample problems, your 1 through 16 has a lot, right? So you can not use the concept you can make. camera goes off, make sure you put that away from me, because we're going to do a little problem together. All right, now go ahead and close that up, put that away for me. You guys have a series of stoichiometry questions we're going to complete together. So you definitely want to write these on your notes sheet. This is not a foldable situation, okay? So just tuck that foldable away, and wherever you've been writing your notes for gases, include this here. So I'm only going to do 3 examples today, and then we'll do 2 more examples tomorrow. Because after that, after you get clear about, you should be very, very proficient, and you can pick up that concept, okay? So, stoichiometry just means what? Just in general, just means what? Come on, guys, help me out here. Conversions, right? Okay, so I'll give you a really generic conversion that we've used a lot. Rice. It's one of our conversions that we use a lot. Right, molar mass, grams per moles. Nana, give me another conversion we use a lot. Okay, so like a liter to milliliter conversion with the metric system. Kendall, give me another. Okay, I'm going to use that. That's kind of separate, because when we talk conversions of stoichiometry, it's all multiplication and division, right? It's a little fence post thing, and we would never do conversions with Celsius to Kelvin. That way we just add or subtract. But that technically is a conversion, so I got you. Maverick, what you think?
Moles and substances.
Right, moles to moles using the balance chemical equation, which is important because we know how to balance equations. We know how to get from moles to moles to something else. Manov, one more. We don't use that very often. Can you use something else?
Liters to mole.
Right, what's the liter to mole conversion you're thinking? And that's of a what? No, so 22.4 liters of a gas, right? So we all remember 22.4 liters of a gas is something that we like to use. But that was only allowed to be used at what condition? STP, right? Standard temperature and pressure. But now you know that that's not always the situation. You know, we've got all these different pressures we could talk about, all these different temperatures we could talk about. So the big idea here is that you're learning when can I use 22.4 liters per mole and when can I not. Okay? So with this scenario, if you're ever trying, and this is just a conversion explanation, if you're ever converting from volume of one gas to volume of another gas and none of the conditions are changing, so temperature staying the same, pressure staying the same, you can literally do one-step conversions versus using the ideal gas law twice, which we ain't got that kind of time. So what you would do is, for a situation like this example here, given I'm providing you, of course, with the balance equation, if 5 liters of hydrogen gas react with 4 liters of oxygen gas, how many liters of water vapor are formed? Let me stick with, actually, no, we'll do it like this. Okay, think about it. Okay, I'm providing you with 2 givens. What kind of problem is this? I'm giving you 2 givens, one for each reactant. The one that nobody likes to do. Limiting reagent, it is. Okay, so we have 5 liters of hydrogen gas and 4 liters of oxygen gas. So let's think about that, and just think about the ratios. Look what you have there, and think about who's going to run out first. Who is my LR? So if I have 5 liters of hydrogen, how much oxygen do I need to react with? Look at this ratio. So if I have 5, look at that. Look at this ratio. Do I need more or less oxygen to react with my?
Yes.
I need a 2-to-1 ratio. Right? So for every 2 hydrogens, I require 1 oxygen. So I need half of the oxygen, right? So if I have 5 liters of hydrogen, how much oxygen theoretically should I need? Half of that, right? 2.5. How much do I have? 4. What's going to happen? So who's in excess? Oxygen's in excess because we just said out loud, okay, I only need 2.5, I've got 4, I've got plenty, I'm good, that's an excess. And so who must be my LR? Hydrogen. So sometimes the thought process with simple numbers is easier than writing all the haves and needs and doing some finagling of ratios if you just sit and think about it for a second, okay? So what we'll do then is, which of these is the important number to use? Hydrogen or oxygen? Hydrogen, so we don't need this mess. This is the starting point of figuring out how many liters of water vapor are formed. Okay, so this is the trick. If you're provided with a temperature constant, like a constant temperature and constant pressure, you don't have to use the ideal gas law. You can just go liter to liter, just like a mole-to-mole ratio exists. Between these, it's a 2-to-1 mole ratio. We technically, since they're gases, can call them liter ratios as well. So all I'm going to do is convert from hydrogen to water and a wet to wet ratio. To what? To what though? To what of hydrogen? Liters. So I'm not talking moles right now, okay? Because we know there is a relationship between liters and moles. So we're literally just going to call this as a 2-liter hydrogen to 2 liters of water ratio. And you could have done that. Like, you obviously can see it's the same number. So if you have so many hydrogens, you're going to make that same number of water. So you're going to be able to make 5 liters of water from this given information. So this is only to be used when wet. I won't say everything's at STP, but everything's at a so a constant temperature or a constant pressure, because they could be on or non-STP. So I just wanted to show you guys what a liter ratio was. Okay, so that's one thing I need to show you. Ready? Moving on. Okay, so again with stoichiometry, you guys talked about mass and moles and liters. So we have a lot of other units that can come into play. This was liter, so we just stuck with that. Didn't have any other units to be involved. So I'm not going to have you write all of this down, but I do think the highlighted parts are the 2 most important things. So if you're ever doing like a grams to mole, moles to moles, moles to volume kind of conversion, you're going to have to at some point figure out am I able to use STP? Am I at STP? Can I use the 22.4 liters or can I not? And that's the breaking point. So if you have STP conditions, obviously you can use moles of gas to liters of gas or vice versa, like we did 3 weeks ago. But if you don't have STP conditions, you have to have a backup plan. You have to use the ideal gas law. The ideal gas law is P equals nRT, which maybe I rearrange it to solve for moles, or maybe I rearrange it to solve for volume. It kind of depends on what we're looking for. But we will have to use that at some point in time and not non-STP conditions. And this is like just a very specific question, so it's like saying solve for moles. And once you get to moles, you can go to grams using molar mass. But this, I think, is very logical to you guys, so don't feel like you need to write that part down. So basically, if I don't provide you with STP, you have to use it at some point. See? Ideal gas law. That's it. STP, use 22.4. Non-STP, use ideal gas law. I'm moving on, because that's literally all you have to write down from the slide. Okay, so this is where we make the decision on what we're using. Provided with all this data, we're eventually going to figure out how much potassium chloride has decomposed. So go ahead and take a minute, write down your data, write down your variables, so give me one important thing, Ariel's table. What variable is that? What variables? Like, what would I title that? What would I set it equal to? P, right. So P for pressure is 755 millimeters mercury. Give me something else, Maverick. I get you twice. What'd you say? The temperature was? So you added 273. 23 plus 73 is 300. Kelvin, good. Camille, give me something else. Oh, that is, thank you. I like to believe you guys. Believe in your math skills. 23. 296, thank you. Camille, give me something else. V equals 42.6 milliliters of, and this is where we have to be clear. This is talking about the gas, right? Well, we don't know what the gas is yet. So I want to put gas right there, question mark, because we need to figure out what that is. There's something else that's important, Hannah. What's here? It may not be a variable, but it may be information. Decomposition of what? What is potassium chlorate? Everybody consult. Write down the decomposition of potassium chlorate. You need the balancing equation. I won't put you on the spot yet. Basically, I need a balanced chemical equation here. You don't have the chlorate. You guys consult with your table. This is why you're in table groups. Consult with your tables. We got that foldable you got too. Not that I want you to, but you have to, and you need it. You gotta have it. All right, Hannah's table. Help me on here. Potassium chlorate. Okay, somebody else pick up from there. That's potassium chlorate. Good. We're going to decompose that. Good. That makes potassium chloride. So any chlorates will make their chloride versions, and we better be making a gas here, right? If you don't make a gas, then you totally have it wrong, because this is a gas law problem, so you have to have a gas to work with. Balance this Riley's table. 2, 2, what? 2, 2, 3. Marvelous. Okay, so now we know what this gas is. So this is O2 gas, if you're going to label that out appropriately. What is the question, Bryce? So when it says much, what unit is it probably asking for? Grams. So here we go. We're going to look for grams of potassium chlorate. And that's our final given piece of given information. Okay, so after we write down our variables, we always then select what? Hold up. We write down our givens. We see a problem. We write down the givens, right? Then we have to select a formula to work with. Well, which formula sticks out right here? Has to be ideal, because we don't have two pressures, we don't have two temperatures, we don't have two volumes. It can't be any of those beginning ones we work with. It's definitely not Graham's law. It's not Dalton's law. It's ideal gas law. So we're going to have to use all this information to eventually find out how to incorporate it into the ideal gas law. Which piece of the ideal gas law do we not have? Period. Moles. We don't have moles, but who would this be regarding? Moles of who? Okay, ideal gas law. So it's got to be what? It's got to be O2. The reason we call it ideal gas law is because it has to reference the gas. So the question in the end is about the solid, potassium chlorate. That is not what N is representing. It's the gas. Okay, so noting P, T, V, we should probably find N, right? Because if not, we can't really go anywhere. Let's go ahead and do that. So isolate N for me. N equals PV over RT. That's, again, I just like to note it's actually gas so we don't mix up our givens in the end. Oh, darn. P's got to be in what? Done. Give me that for me. 755 divided by 60 millimeters of mercury. 755 divided by 60 millimeters of mercury. 0.99. Can you give me one more decimal? 0.993 ATM. Okay, so 0.993 ATM. Everybody, what should volume be established in? So tell me that in liters. So we're backing up three places. So 0.0426 liters divided by, everybody R. You got this.
0.082.
Recite it.
0.082
atmospheres times over
moles times
Kelvin. Okay, so we have that memorized. And then what's our temperature? 296 Kelvin. Okay, so what units should cancel here? Atmospheres on top and bottom. Keep going. Top and bottom liters. Good. Kelvin top and then the bottom of the bottom. So moles, good, is the only unit remaining. Somebody help me out here. Should probably be a small number. Bailey, you got me? Trying to see if I can get my name card started back because you guys are getting lazy on me. What you got? 0.0017. Can I get one more? Did you calculate this? 4.41 moles of oxygen. Okay, so this is not our final answer, so I'm not even regarding sig figs because it's going to be used in just a moment. All right, guys. So check. We have to solve for oxygen gas. How in the world am I going to get potassium chlorate? Stoich, mole ratios, very good. So you have a mole of a certain number for oxygen, and if one wanted to go from oxygen to potassium chlorate, what do we have to use? What about the equation?
Like the balance, the ratio.
The ratios, right. So we have a 2 and we have a 3. So that will just Stoich from here on, okay? So solve that in your group. I think that's right. And can you tell me the molar mass of potassium chlorate?
126.5.
0.55. All right, and then drum roll when you're ready. I think we'll be around what? Point 2 something? No, what is it? 0.142 grams. You rounded, right? Okay. And it looks like 3 sig figs all around. Okay, so that was a doozy. We read, we saw data regarding gas laws, and then with that gas law, we also had a decomposition reaction that made a gas. Once you see both of those things start to come to play, and then you'll notice your question is not about the gas, you're like, okay, I've got to solve for the gas information first, and then I'll use stoichiometry to get to the non-gas items, so like the potassium chlorate in this example. So this one we did ideal gas law first, then we did Stoich. Other questions we might do Stoich first and then ideal gas, but you will usually use both of those unless it's at what? STP, and then we're like, hey, we don't have to use ideal gas law. What can we use? Just simply the 22.4 liters per mole, and that's for a gas. All right, so let's do, yes, okay, you guys start this one. Write down your givens. So there are 5 lecture problems that we do here. Usually I do a couple now that you guys do the rest at home. I'm trying to see if I can keep sticking with you in class on these. They get a little challenging, so pay attention, write down what you need to, write down everything really. after you write down your givens, you guys kind of want to talk about how you would like to address this problem in the curriculum. Do you want to have your gas offers, or do you want to do story? Talking to your group about the steps you might take. Maybe think the whole process through before you fully get into it, because you need to have a game plan to make sure you're going to be able to get to percent yield. See at least a minimum some conversions or some making appropriate units to utilize for an equation. If you're stuck, here's what I'll tell you. Percent yield, we know that. What's the equation for percent yield? Say again, low and pro. Actual yield over theoretical yield times 100. All right, so essentially you've got to get both of those values to solve. So what information could technically give you theoretical yield, and what the heck are we yielding? What are we talking about here? What are we yielding? What gas are we yielding? Oxygen, O2 gas, right? So how would we, like, what data point would provide us information that could theoretically yield of oxygen gas? What data point? Remember, theoretical yield is like, if I reacted X in La La Land, in perfect world, like I would get Y, like I would get this much product. The initial reactant controls the theoretical yield. So that magnesium, 4.5 grams of magnesium chloride is controlling the theoretical yield of all of its products, because we're pretending that's 100% effective, right? So you have to use 4.5 grams of magnesium chlorate to get that guy. And then how would one get actual yield of the same thing? Remember, because this is, for us, you guys probably are going to you'll go to some unit of oxygen gas. Okay? How would one get to actual yield of oxygen gas? Like actually in the lab. Come on. All right, I'll let you guys talk. You guys are talking to me. I'm going to read your mind, so you can't talk. There's only one other really thing you can do with the data provided. Camilla, what's an ore master? 90. If you are done, you can proceed to number 2, which is on your lecture note sheet. you are good. You can proceed to number 2. If you need to look up here for the thought process behind it, I'm ready to kind of walk through this. Those of you who went to moles or grams of oxygen for either actual yield and theoretical yield, as long as it's the same unit, you can make a comparison. So I opted to actually go with moles just to show an alternate route. So again, we need our balanced chemical equation. Check. That's the only way you can get from the gas to the individual solid given information about. So theoretical yield comes from la-la land. If we have a given reactant, it goes through stoichiometry to provide us with information about how much product can be yielded. I actually ended up using the oxygen moles as my theoretical yield. You could have also just as well used the grams of oxygen as your theoretical yield. The only other data provided was ideal gas law data. You have to see that. That's where I'm trying to get you to see. You guys are just sitting there just not trying. Some of you guys are waiting for me to do the whole thing, and you cannot depend on that. If you have P, T, and B, there's only one gas law that you can use, which is the ideal. Noting that it is a gas law, you do solve for moles of the gas. So that's the important part. You solve for N, which is moles of gas, and that was your oxygen gas here. This is in a lab situation provided with pressure, temperature, and volume data. That's like experimental, which is your actual yield. And then, as you know, actual yield over theoretical gives you percent yield. So by doing that, you solve and get about 97%. Okay? All right, look at your lecture notes for number 2. The lecture notes are in the very bottom, right-hand side. Yep, bottom right-hand side. Same process, guys. You have a Stoich relationship someplace, and you have an ideal gas law relationship someplace. You just have to organize your thoughts and try to think it through. I'm basically making you problem solve. That's the purpose of this activity together. This is also on the board if you cannot find it for the first time. we should have our data down for this one, and we should probably have a reaction. So let's get that reaction. Let's see here. Linear's table, help me out. What are the reactants here?
We're gonna have magnesium, so it's gonna be Mg plus hydrochloric acid, so it's gonna be HCl.
H what?
CL.
HCl. Okay, everybody, what kind of reaction is this when we have a single and then a combined compound? Okay, this is all single replacement. ST table, pick up from there. Magnesium chloride and okay, and we balance that, so pick up. Okay, so we have a balanced equation. We have data provided about grams of magnesium, molarity, and volume of HCl. Okay, this is a telltale sign of what kind of problem when you're provided both reactants with both data points. Say again? It is limiting reagent. We have got to approach that first, but let's think about why we have to do that, okay? So in the end, the question, or the data provided, so this is an LL problem, okay? The question is asked of how much gas is produced in volume. We're provided temperature data, pressure data. Then it says the student captures a certain milliliter of that volume of the gas and asks for percent yield. So let's think the whole shebang through, okay? We're just asking for percent yield. So what does that really mean we need? Okay, so we need actual yield and we need theoretical yield. We're going to multiply that by 100 to get percent yield. How would one get to actual yield from all of this data? Help me out here. Shout out, people.
4.15 grams.
Well, so actual yield is experimental, right? So that means that's captured in the experiment. Say again? They literally tell us the actual yield, right? So when it says the student captures that volume of gas, check, we already have the actual yield. You just need to make sure, like, you identify, you know that already. So then the real question is, what's the theoretical yield? So it's asking for a theoretical yield of what? Hydrogen gas, right? Because it says they capture the volume of said gas, which is hydrogen gas. So we have to talk about the exact same things. We're looking for milliliters or liters or whatever volume of the hydrogen gas. So the real question here is, how do I get to liters of hydrogen gas? Well, we kind of already knew that was our question, so that's what they asked us right here when they said what volume of gas could be collected, right? So how am I going to get to liters of hydrogen gas from all of this data? We have P and T. We don't have enough to use what yet? We don't have enough to use the ideal gas law yet, but we're close. What are we missing? What do we need? The moles, right? So we need moles of what? Hydrogen gas. So before we can get to this question, finding volume, we need to get to moles of hydrogen gas. Now, what data would help me finally get to moles of hydrogen gas? Maybe moles of magnesium, or it could be moles of the other reactant, right? So this is why it's a limiting reagent problem, because we first need to figure out which of these moles of either the magnesium or the hydrochloric acid is going to control our product, is going to control the moles of hydrogen gas made. Okay, so this data is going to help us find moles of hydrogen. We'll use that, find B, and the ideal gas law, compare actual and theoretical. Okay, here we go. You guys are my calculators. You ready? 1.15 grams of magnesium. Get me 2 moles. What's the molar mass? 24.31 grams of magnesium. And that's moles of magnesium. And how many moles of magnesium do I have? Shout it out. Come on. Like, calculate.
0.047.
And that's moles of magnesium that we would call have back. This is throwback to limiting reagent, so this is the language that we like to use for that. Okay, so thank you, STs. You're off the hook. I need somebody else. I need to get to use this information about hydrochloric acid. How am I going to use that information to get to moles that I have? Hannah? So I'm going to multiply, you're telling me to multiply M times V, right? Molarity times volume, but volume must be in what unit here? And this is liters of a solution. This is not of the gas. So we would never use that for like V in the ideal gas law. So 0.1 moles of HCl over 1 liter is what that right there means. That's molarity again, moles per liter. And when I multiply by liters, liters cancel, give me the moles of HCl. So how many liters is that? 0.150 liters. What you got done? 0.015 moles of HCl. We call this one our what? This is an LR problem. I've titled this what? This is how much I have. I had 0.1 molar and I had 150 milliliters. I have this much HCl. Okay, who's my LR? We don't know yet, right? Okay, we don't know. So how do I figure out my LR? Okay, this is a different table. Crowell's table. Notebook's got you. Ryan's table up here. I have and have. What do I need to figure out next? How do I figure out my need? Raise your hand if you know where we're going. Call it a friend real fast because I gotta move on.
Mole ratios.
How do I incorporate that here?
So you multiply that by 2 moles of HCl.
2 moles of HCl from the 2 here over
1 mole of Mg.
1 mole of Mg, and that cancels out the Mg to give us, we need, what does that comes to?
0.0946.
0.0946. Alright, so we need this many moles of HCl, 0.0946 moles of HCl. I'm immediately going to compare, just because I'm running out of time, compare that to how much you have of HCl. What's going to happen? Okay, is this lesser or more? Way less, right? So what's going to happen? This is limiting reagent, this is less, I need a whole lot more, this is going to run out, I know this is my LR, proceed. Now we know how to get to moles of H2. That's our real question here. So what of these values am I going to use to proceed? Your half of HCl is the most important number on the board right now, so we're going to move on. And that is controlling the product of hydrogen gas. So if I have 0.015 moles of HCl, what was the ratio? Mine's hidden away. So 2 moles of HCl for every 1 mole of hydrogen gas, and that's going to be 0.0075 moles of hydrogen gas. Hallelujah, we have an N value, and you're going to proceed from there. That's your N value. Find everything else. We kind of talked about that. Expecting you're done with this in the next 3 minutes. You can listen to your ancient line with your light connection. So the oxygen meter will be able to do that. You can just break the data. talking to your table roots, because I have already explained on the whiteboard over here how to proceed. You're sitting there looking at 0.07 black holes.
This equation. Volume. Which basically
From 42 divided by 7.
0.9763 atmospheres.
Right, you guys are, I want you to at least write down the givens for 3, and then we'll do 4 and 5 in class tomorrow. Minimum write down the givens, there's probably a balanced chemical equation that's related, and even thinking about the problem-solving process would be required. Calculate this crap on your own. I am not your human calculator. You guys can do this. You need to follow through with the thought process that we mentioned over here.